Well, I mean, you remember that one time we had it in butter though, the projector kept on like blinking out.
Yeah, that's right. But these like until like a day before I get off.
Our first meeting last fall, the entire screen would just flip in out and begin to light up.
I felt so bad for the older guy we had there. I mean, I could, that was breaking his concentration.
Yeah, I was so nervous.
I don't know how, like, I mean, I don't know, I guess everybody gets nervous about something, but I just feel like if I was that much older than I used to be, no kids. You can talk to kindergartners all day, man. He literally was like, yeah, like, you guys are seeing over here, 115, how would you do that? Pretty good.
Yeah, it was just Mr. Force, he was one of the
Yeah.
spilling all the dirty details and stuff about all the things that went wrong and discussion behind the words.
It's not fun.
Yeah.
You get like, I'm expecting a pretty small crowd.
Good job.
The physics in the also long is like 90%. It's because everybody's in Europe.
I just don't want
Their
to
dog
see
is
that
there.
long
It's like,
if I would want to go
it's like
to
me
that
and
area.
one or.
And it's also not as technical as.
So let's talk
Arrow.
Yeah.
No, in the non.
Oh, okay.
In non-air, I think it's exam, so.
You're recording this basically.
Okay, it's being recorded.
That's what happened to us with physics and Open. Open was supposed to win next week. And he was like, so I don't want to you guys with exam on students for it.
Yeah.
That would suck.
Yeah, so
If you
kinda got
read
into
I'm like,
it,
I mean,
but
sure.
we
we need to study material.
They start
It's a week after our it's been like
Yeah.
2 weeks instead of 3 weeks.
I was hoping it would be a month.
Collins is like, I'll give you a cheat sheet. That makes
So I think I'm
sense.
just gonna apply to one job every couple of days. And just keep
Wait,
reporting.
it's not amazing.
No, I've had, first week of this month, I had physics. This week I had chemistry, next week I have math, and the following week I have another physics.
One of the either part two to stay during COVID. And it took them like 3 or 4 months.
You said you could
apply
use a
to
second
a
side
successful
class.
position. But the other guy.
I was like, you're not putting me with confidence.
And that week after he applied, he had his first interview. We got him.
Okay, so what y'all are also the answer, I'll probably
So-
make.
Yeah.
Oh, what is the word for it?
Good outcome.
Okay, so y'all are a little
I should probably be grading, but.
I mean, we are, and we're not, we're doing like those analysis.
It's more important that you.
Y'all are getting like right
I don't know.
synthesizing.
Well, we're doing it, yeah,
I
we're.
don't
we're
think Colin
just
even took
what?
the question on homework
College
that she needed
finished it Tuesday,
to do, so.
but then his computer wasn't working,
Even
so it's with lecture didn't work. So it was like, it's almost like, I'm just giving you guys some material.
There's still more to come.
Cool.
He's a good dude, though. Collins is really nice. I think he really like cares about
Oh,
his
that's
material. But I
I
think
was like
that
studying
in
for,
some
but
ways,
actually was like.
that means like he has like the absolute hardest
Eighty
papers, like that are
like
fair. I've
We're
never,
good.
will not say that any of his tests have been unfair.
Reduce the
They're all fair, but they're
Threshold
maximum
for-
difficulty possible.
Yeah.
Before you reach
What
the
it-
odds, that's not fair.
I could fight for an A. if I
Alright,
made-
so, go ahead and
if
get
I made it.
started. Y'all have not yet, go ahead and sign in, even though there's not too many of you. So there is some information questions regarding next semester too, so look some input.
Input for what?
Hmm?
Input for,
For like, if they wanna see anything for the next semester,
oh,
do
right,
any
right.
events. Requests for speakers, anything like that. So since it's their final general meeting.
Oh, yeah.
Thanksgiving and Christmas.
Cool, quick agenda, same exactly as last time, again, if you wanna connect with us, if you haven't already, do that. And then just some highlights from last month was our Halloween party. Kind of small turnout, but it was still really fun, we ended up watching a movie for a good hour and a half, thanks Bryce. But gave the idea, we're probably gonna do it movie night for next semester, so that. Then some space fishing. Callie or Connor, would you all like to say anything on this topic?
Oh, yeah, it was fun. Went to lots of, like, the first day was packed because we were basically doing tour after tour for the entirety. We went to the Goddard Space Flight Center and went to the National Air and Space Museum. This is a whole new Apollo and Mercury and Gemini exhibit there. Yeah, good stuff. With Space Vision, Kelly was moderator for a panel. Talk about
Yeah, space medicine panel. It went really great. Yeah, there's me doing space medicine panel stuff. It was really fun. It's a good trip. If anyone gets a chance to go next year, it'll be in Denver, Colorado. So that'd be cool.
And we finally, after like 3 or 4 weeks of fighting for this, got the green light. We do have a rocket competition on Sunday.
Let's go.
12 p.m. fan filled. Look for the 10. A bunch of people randomly walking around. I don't know exactly where on Fanfield we are yet. Once we get an actual location, we'll send it out so everybody can find us. Otherwise, it should be pretty easy to spot us. It's gonna be a fun field. So come out, have fun.
How close can we park to where stuff is going on?
I'm ready. You want?
Yeah.
Right. Used car.
All right. And our lovely speaker for the evening, Dr. Selva.
All right. Thank you, guys. I think I have a few slides, but we can hopefully keep it pretty informal. So I guess just for my benefit, I know there's a couple of arrows here, but what are the other non-arrow majors that are represented here? Chemistry or what? Chemical?
Secondary science education.
Okay.
Kinesiology.
Agricultural economics.
Okay, so a little bit of everything. Okay. Cool, yeah. So again, I wasn't sure what exactly was appropriate, so I'm just going to talk a little bit about what I do. So, using AI for space stuff, specifically for designing new space mission concepts, and for also what we call onboard AI, so more on the operational side of things. I guess I'll just start with a little bit of kind of my career. I figured maybe you prefer to hear about kind of like my journey than my research. So since I wasn't sure, I would start with this as a kind of a longer introduction. So I'm actually from Mallorca. Mallorca is an island in the Mediterranean, east of the mainland. These are some pictures from Mallorca. If you've never been there, highly recommend it. Cheap tourism. It's not too expensive. You can get to Europe. Getting to Mallorca and staying there is actually pretty cheap. And as you can see, the beaches are very nice. There's a lot of cool stuff. I played a lot of tennis growing up, but I'm still terrible. I wanted to be a tramway conductor when I was a kid. Pretty much failed at that. When I was 14, we moved to Barcelona. Maybe some of you have been to Barcelona. It's a definitely more popular place. Very beautiful, close to the sea and the mountains. It has really everything. I did a bunch of chemistry, like I was telling you. I went to the chemistry Olympics, and yeah, I don't know any chemistry anymore. I was in a student organization like you guys. It was called AESS in Barcelona. We did space stuff and also like robotics and those kinds of things. I had a lot of fun with like robot competitions, and we did like little conferences and things like that. One of those opportunities got me basically a chance to go to Toulouse to the International Astronautical Federation Congress in 2001 in Toulouse. And then in 2002, thanks to my 2001 gig, I was able to come here actually to Houston for the IAF 2002. So that was my first time in the US, was back in 2002. I was 21 or so. And I presented a paper on like super hardcore math, like hardcore calibration of two-dimensional interferometric radiometers. Like I didn't really understand everything that I was talking about, but I had a lot of fun. After that, I got into remote sensing. So here, this is a campaign of measurements that we took in Valencia in the east of Spain. This is probably 2002 also, something like that. And what we were doing is basically trying to do that calibration of the radiometer. So we had like a little antenna that was like a meter by meter square, basically. That was an L-band antenna. And the radiometer is basically just an antenna that listens to nothing, listens to noise, basically. And then from the microwatts that you get, if you're really smart and have really good models, you can get some information about whatever it is that you're pointing at. So in this case, we were trying to get information about the soil moisture, basically, based on the radio frequency that we were getting, the L-band noise, essentially. So that was actually pretty fun too. This is me doing a lab, trying to basically do some coax cabling stuff. It was less fun. After that, I went to Toulouse. So Toulouse is in the south of France. They have this school called Super, which is a pretty nice school in Europe for aerospace engineering. And I was actually studying something else in Barcelona. I was studying telecommunications engineering, which is similar to electrical engineering, I guess. I'm very multidisciplinary, like maybe some of you. And I really wanted to do space stuff, so I went here. And it's also a very nice place. If you have not been to Toulouse, you know, wonderful place. This is a picture of the school. They had a few of these aircraft from World War II or whatever. I mean, it's like pretty cool stuff. They do mostly aircraft stuff in the school, but they do have one master's program that's pretty good in terms of space. I actually ended up doing, it was pretty random, but I ended up doing my essentially master's thesis, more like a bachelor's thesis, really, on aerodynamics of compressors, which was very random for me. So I graduated, so that was 2004. Graduated with my dual degree thing, electrical engineering and aerospace engineering, and then I got hired by this company, Ariane Space. And if you're space nerds, you probably know what Ariane is. It's the name of a rocket, right? The name of the European rocket, Ariane 5. Now we have Ariane 6 coming up. So I was basically an avionics specialist for the Ariane 5 launch team. And it's a pretty cool job, actually. So you do a little bit of training in Paris for about 5 months. I was in Paris. And then they ship you basically to French Guiana, to Kourou, which is where they launch their rockets from. So this is in South America, like west of Brazil, northwest of Brazil. And it's the jungle, as you can see. And I had a lot of fun. I did 21 Ariane 5 launches, you know, very operational job, basically doing the integration of the rocket. The rocket comes by pieces to Kourou, and you know, they integrate it there, and then the satellite comes, and then they put the satellite on top of the rocket, and then they put the fairing, and then we do all of the tests, and you know, put all of the propellant in the rocket, and then we launch, right? So the whole thing takes about 2 months. And I guess I was more on the electrical and software side of things, but still, you know, pretty close to, I mean, really touching really the rocket every day. Of course, the best thing of that was the final chronology, the countdown, you know, the last, you know, 10 hours or so of operations, you know, high pressure, a lot of stress, you know, you can't have a delay, because if there's a delay, it's, you know, $100,000 a day is basically the cost. So it was very fun, but it was also very repetitive. So in 2006 or so, I started to see that maybe that wasn't for me, you know, operations, checking steps and procedures. I mean, it's a lot of fun to touch the rocket, but, you know, a little bit repetitive. So I wanted to do something more conceptual, more, I don't know, early on in the design process, in the development process. So I decided to do a PhD. And I went to MIT. I applied to MIT, and somehow I got in. To this day, I have no clue why I got in. But that's where I did my PhD. I was there for 4 years for my PhD and 2 years of postdoc. And I was working basically on space systems engineering, really looking at Earth observation satellites, so like weather, climate, land imaging, you know, looking at how to do basically optimization of what we call portfolios of missions. So you have, every mission is not just like a single mission. It's a mission in the context of a whole program, right? So trying to optimize the design, not of a single mission, but of a whole portfolio of 70 missions, as provided by the 2007 Earth Science Decadal Survey. So that was a lot of fun. I learned a lot about optimization and AI, and that's really where my passion for AI started. I started working with different flavors and kinds of AI, from very old AI, something called rule-based systems. That's more like the kind of AI that we did in the 1960s. I don't know if you guys have heard about, like expert systems, knowledge-based systems, the kinds of systems that, play chess, for example, right? Like chess playing machines and things like that. And then, of course, when I was finishing my PhD, we started to have kind of like the machine learning revolution, and machine learning started to be really popular. So I looked a little bit into more machine learning kinds of paradigms. But that was a lot of fun. This is where I lived. To this day, I don't know of anybody, like 0 people, that paid less money than I did for my rent in Boston. I paid $570. We were 3 sharing this house, which was a very crappy and old house. There were some stains on the carpet that we really don't know. I mean, we have some ideas about what that could be, but we really, anyway. And then the other thing about this house is that this right here, you can't really see, but this was kind of like essentially a crack house. I mean, it didn't really have a roof. It was just like an unfinished house where some guy lived. It was, anyway, we had a lot of fun. After my PhD and postdoc, I was hired to be a professor actually at Cornell University, so in Ithaca, New York. So I spent 4 years there. That's actually where our first daughter, Emma, was born. I was in the mechanical and aerospace engineering department there. I met a lot of incredible people. Mason Peck, former chief technologist of NASA, was my mentor there. Anyway, it was a lot of fun. But then 2018, basically my wife, who's also a professor here, Professor Anadia, she was heavily recruited to come here. So, we both came and visited, interviewed, and in the end, we got offers, both of us. So that's how we came here. So that was in 2018. So it's been 5 years as an assistant professor, and then now I'm an associate professor, I guess, in September. If you're an aero major, maybe you've had me already. I teach a lot of systems engineering, space, and AI kind of stuff. So 41, 42, that's our capsule design. 424, that's our spacecraft dynamics class. And then I taught a couple of 489, so those are like special topics classes for us. And I'm teaching one right now, which is the foundations of autonomous aerospace systems, which is kind of like AI for space vehicles, essentially. Well, it's really an AI class, but with the excuse of aerospace. We had another daughter along the way. That's Olivia in the front. I'm in the back now. So Olivia's a Texan, and then Emma is an Ithacan. And I'm becoming a U.S. citizen on the 1st of December, so that's exciting too. So that's a summary, basically. I mean, if you track where I've been, where I come from, this is Mallorca. And, I went to Barcelona, Toulouse, Paris, Kourou, French Guiana, Boston. I did a gig at the European Space Agency in the Netherlands for a summer. Ithaca, now here. That's me. All right. So that's the journey. And then I don't know how much time I have. 10, 5?
It's 7:18 right now. You have until 7:45.
Oh, okay. I have time. Great. So I just wanted to give you guys a little bit of an introduction to my research. So my lab is called the SEED Lab for Space Systems Engineering, AI, and Knowledge. So really we work somewhere in this Venn diagram. So if you're a student in my lab, that's the kind of stuff that you learn. Space systems is our bread and butter, is the beginning of everything. So we tend to work primarily with early formulation of space systems. So I don't know if for the aero majors, the name SMAD may sound familiar. SMAD is the Space Mission Analysis and Design textbook. That's kind of like Bible #1 for the students in my lab. Bible #2 is Russell Norvig, which is the AI textbook. But yeah, so we've done a lot of stuff related to space systems, primarily Earth satellites. So Earth observation, of course, because that's kind of my background with the remote sensing stuff. Communications, I also have a background in RF communications kind of stuff. But I've done, many other kinds of work with space systems, also with robotic exploration and also human spaceflight. I'm mostly interested in kind of like new architectures and new mission concepts. So what if instead of one big satellite, we had 100 smaller satellites, and instead of the satellite not really doing anything interesting, maybe those 100 satellites are doing onboard data processing and talking to one another and being highly autonomous and those kinds of things. So the AI, of course, knowledge-based systems, AI systems, machine learning, global optimization, multi-agent systems, all of that stuff is the kind of stuff that people learn in my lab. And then the design and systems engineering aspects, so design optimization, model-based systems engineering, formal system modeling, that kind of stuff. So really that's what drives me, really, is that kind of stuff. So this is what we call a sensor web, an Earth observing sensor web. We don't have this today. This is what I'm trying to study and to push towards. So this is the idea of having satellites talking to other satellites and also talking to UAVs and HAPS, high altitude platforms, and ground sensors, and they're all making onboard, doing onboard data processing with the images that they gather, and making autonomous decisions and talking to one another to coordinate. That's kind of the kind of vision that kind of motivates me. So we do a lot of modeling, simulation, and optimization tools related to these kinds of systems. We've done, especially from the AI assistant side of things, I don't know if I'll have time, but I can show you one of the, I guess, classes of projects, because we've done many of those related, is about using AI assistants, basically having an AI peer to do some of these tasks, like a teammate. So from that perspective, I got pretty deep into human machine teaming and human AI collaboration. And then more on the planning and scheduling side of things, machine learning, the other kind of AI, that's more like onboard AI, that's really for operational stuff, primarily, basically to make these systems more autonomous, more responsive, and just smarter overall. But yeah, idea is to be able to demonstrate these new concepts, these new missions, these new concepts that we come up with in actual flight programs. And this is something that I've been able to do recently a couple of times. I was involved in a mission called Tropics. That's a constellation of 6 CubeSats. You guys know CubeSats, probably tiny satellites, Kleenex box size, that we use for tropical storm monitoring. Basically, they have kind of like that radiometer that I was showing, but instead of being a 1 square meter, it's like a tiny little thing, like 10 by 10 centimeters. And they measure at higher frequencies, and we can use them to measure liquid water, and essentially precipitation. And I'm also involved with basically mission concept studies, as we call them. One for remote sensing of water quality that a lot of students in Aero have done 401 project related to, and now one related to basically something that looks like this called 3D chess. I'll show you a little bit about it if we have time. So just a couple of examples, I guess, of these different flavors of research projects. So I guess I can start here. So that's the onboard AI side of things. So recently we've done a lot with developing planning and scheduling algorithms for Earth observation satellites. So nowadays, Earth observation satellites are not very smart. Basically, they're just looking down. They're pretty boring, looking down and just taking images as they go, storing the data on board. waiting to be in visibility of the next ground station, and when they are, they just dump all the data they have and rinse and repeat kind of thing. But if you have the ability to steer your satellite, which we do now, we have miniature reaction wheels and those kinds of things that are pretty powerful. And if you have some ability to do onboard data processing, to do things like detecting events of interest, for example, in the images that you're taking, and if you have the ability to plan, and to basically planning means deciding what to do and when, right? Autonomously, the satellite can basically change its ConOps and decide what to look at and when based on the data that it's acquiring in real time. And that's a game changer in terms of the ability to respond to things like fires or storms or even more scientifically interesting things like, oh, I want to catch the exact moment of an onset of an algae bloom in a river, or I want to catch the exact moment of cloud formation, which is basically short-lived processes that if you're just using Landsat or something, you have essentially zero chance of just getting by randomness, right? But if you have some ability to process your data and you have some predictive models that are fairly good, you have a much higher chance actually of capturing those events, which is pretty cool. Something that we're trying to quantify right now. I'll show you what that looks like, hopefully in a couple minutes, but you can see in that little animation there, those are a bunch of satellites, and the lines between the satellites, those represent communications through crosslinks. Basically, the satellites are talking to one another about what they're seeing so that they can change their plans accordingly and essentially coordinating as they go completely autonomously. So I guess let me go back. So that's one flavor of projects. If you're more interested in getting closer to humans, I guess. So I guess in this case, we're trying to get the human out of the loop, right? In a sense, to the highest extent possible. Here, we're actually much more interested in this synergistic collaboration between the human, which could be a ground engineer, or it could be an astronaut. We have different kinds of applications. And then some kind of AI agent that's supporting that person in whatever mission they're doing, right? So these are called AI assistants, cognitive assistants, virtual assistants, digital assistants. They go by different names. I used to say, think Siri or Alexa, but for space. But now should probably be ChatGPT or something like that. It's way more accurate in terms of the capabilities, right? Because let's face it, Siri and Alexa were not very smart. I mean, they were just very restricted in the number of useful questions that you could ask if you're thinking about a specific application, like a space application, right? Now with ChatGPT, it's not more open-ended, right? But we've done basically conversational agents that you can talk to in English, and they can do data processing in the background. They can answer questions about space missions, Earth observation missions, communications missions. They can do design of some aspects. Can you design me a power system with these requirements? So we've done a lot of those things, spanning really the entire development of the mission, from early design to operations. And I'll show you an example of kind of like the very end. One of the projects that we've been doing for 4 years now, or 5 even, it's basically doing one of these virtual assistants to support astronauts when there's an anomaly on board of the spacecraft. So we've tested one of our agents at NASA Johnson in the Human Exploration Research Analog Facility, which is kind of like a piece of the ISS, a little module that they have there. So we put people there like 45 days at a time, 4 of them, and they do all sorts of studies on them, like sleep deprivation and exercise protocols and all those kinds of things. And one of the studies they did in the last campaign was playing around with our Daphne agent, as it's called, and basically trying to resolve fake anomaly scenarios like, the carbon dioxide removal assembly failed, so ppCO2 is increasing and oxygen is going down. What are you going to do, kind of thing? So they do that with our agent. Without our agent, we look at different metrics, basically how long it takes them to resolve it, and things like situational awareness and mental workload and those kinds of things. So I think those are the two that I probably have time to briefly show you. We do other things more related to space mission design, like space system studies, and more like theoretical human machine teaming stuff. But if you guys have questions, I guess you can ask. Let's see. Until 45 is so 3D chess. That's the one where we're doing the sensor webs. So I don't want to show everything because it would take forever and I don't want to bore you to death. But I think you guys kind of get the idea. So this is what we have today. So I kind of explained these already, but basically we have large monolithic satellites that have no onboard data processing capability and essentially are like dumb boxes, for lack of a better word. I mean, extremely sophisticated in the measurements that they take. It's just that we choose not to have any communication between them or any kind of like data processing or anything like that because, we have been very risk averse. This is what we're going for, right? So it's a dynamic network of sensors basically that are context aware, that can take measurements of their surroundings, that can reason about their own state, about their own capabilities. They can accept new mission objectives, dynamic mission objectives. They can reason about other agents' capabilities, and based on all that information, kind of like come up with a plan in a completely autonomous and decentralized way. So that's really chess. This again does not exist today. This is TRL2 basically right now. That's jargon for nobody knows if it will ever work. But we're doing a bunch of simulations to look at one, the feasibility of this, and two, okay, assuming that it's feasible, what do I actually get out of this? What is the extra scientific and societal value? Can you quantify it in terms of, I don't know, number of fires observed that you wouldn't observe otherwise, or number of those scientifically interesting events of interest observed that you wouldn't be able to observe otherwise? So that's what we're doing. And just to explain how this would work in terms of the actual ConOps. So here we have our little sensor web. It could be all satellites, but it could also be a bunch of satellites, UAVs, ground sensors. The idea is that every agent is doing whatever they're doing, the fog mission, background mission. And some of these nodes, they have data processing capabilities. So they can do things like transform the raw data that they get, which is essentially radiances in different bands, and transform that into actual geophysical parameters like chlorophyll concentration in a river or in a lake, right? They do that in real time, right? Which is pretty cool. And then they can do data analysis, trend analysis to basically determine that there's an outlier in a chlorophyll A measurement, right? And then based on that, they can generate a task request to study these events of interest, right? They will generate that task request and send it to the network. They will broadcast it basically to the network. And then the other agents in the network will receive that. Let's say, potential algal bloom at a specific latitude, longitude, with a specific severity, maybe based on the fraction of lake area affected, maybe based on nearby population, something like that. The specific task request is to measure specific parameters that are related to an algae bloom, like the water level, the temperature. And there's a timeliness to this, right? If you take too long to measure this, since the moment that you've measured the chlorophyll, then those measurements are decorrelated from one another. It doesn't mean anything anymore because it's too far in time. So it needs to be within a few hours. The other satellites then receive the task request and they have the ability to reason. They have a knowledge graph, basically, which is kind of like a database of knowledge. So they can see, oh, I need to measure these parameters so that I can understand algae blooms. How does that compare to my capabilities? I know that I have a thermal infrared sensor, for example, and the mission is measuring water temperature. So that doesn't appear to be a match, right? Thermal infrared gradients is not the same as water temperature. But if you're able to reason, if you're a human being who knows about these things, you know that actually you can infer water temperature from thermal infrared gradients. So thanks to this knowledge graph, doing some reasoning, you can infer that there's a high probability actually that either you or someone else, doesn't even have to be you, right? Can actually later infer water temperature based on your measurement. So you're going to determine that you can actually perform this task with some performance and some uncertainty. And then among the agents that have decided that they can somehow participate in this task, they're going to enter basically a decentralized coordination stage. So basically they're going to decide who does what. Okay, so there's a bunch of people that can take this thermal infrared measurement. Who is in a better position to take that measurement, as opposed to, doing something else for some other task request, for example, right? So this is a decentralized task allocation problem mathematically. And the way that we're treating this right now is a consensus-based kind of approach. So this is essentially like an auction where the agents bid for the tasks, and they bid based on the expected utility that they think they can provide for that task. So based on their sensors, on the task, on their state, where they are relative to the location, all those kinds of things, they put all of that into a big model that spits out the number. That's basically how good a job that agent thinks they can do with the task. And then whoever has the highest number should win in theory. The problem is that this is complicated by the fact that the agents cannot talk to one another all the time, because there's not, constant line of sight here. They don't have constant communication. There's a latency when they do have the communication. So just deciding who has the highest number basically is actually a harder problem than it sounds because of the communications issues, but that's kind of the idea. And then, once we have decided who's going to do what, they go ahead and replan. Basically, they update their plans. They do what they need to do, and then they continue, keep going, basically. So that's kind of the idea behind 3D chess. So what we've done is build a pretty massive multi-agent simulation tool where each agent is one of these sensors, basically one of these platforms. It could be a satellite or a UAV or a ground node. There's a special kind of agent which is essentially modeling Earth. So you can ask this agent for the state of, say, water temperature in a given river, and it will give you that value, right? So we're just modeling the gathering of the data collection. Yeah.
Could a boat be one of the agents? Imagine you have some kind of boat for the Navy or something that's trying to connect with the satellite.
Yeah, absolutely. I mean, we haven't done anything with boats or any kind of sea agent. We haven't really done anything related to defense for this, but you can see how this applies also to defense kind of problems.
Are you assigning weight to the considerations for the number? You say, okay, this sensor is better, or we're going to say this has a 10 weight versus something.
No,
the system does that.
I mean, in a sense, but instead of it just being an arbitrary weight, these numbers actually come from science models. So that's kind of a little bit of the devil is in the details here, right? So a lot of prior work in task allocation similar to this is based on essentially what you're saying. Okay, so this task has a value of 2, and if it's done by this other agent, it has a value of 3 or whatever, right? So it ends up being a relatively benign mathematical problem where you just have a matrix basically of agents and tasks. These are the values for each agent for each task, and it's still actually a pretty complex problem in terms of the it's an MP hard problem and things like that. So it means that you can't solve it very efficiently. But it's very easy to understand. The problem with that is that it's not reality, right? Because how do you come up with, this agent for this task is a 2 or a 3 or a 4? Well, it's actually very hard. It depends on what is the type of sensor on this satellite, what is the geometry with which it's looking, what is the range, the distance, time considerations, how long ago did the task request, start, spatial resolution, signal to noise ratio, temporal resolution. It's just a lot of different things, right? So we have this science model. We have actually a bunch of scientists in this project, and their job is basically this bottom row here, coming up with those science value models, onboard processors, and predictive models, so we can, come up with those weights in a way that makes sense, right? But yeah, I mean, other than that, that's kind of the idea. So we're modeling the network as agents that exchange messages, basically, is the idea. So we've done a lot of simulations actually with different kinds of configurations, more satellites, fewer satellites. We have like a flood in the flood scenario. We have an algal bloom scenario. We have scenarios with satellites, scenarios with UAVs. But essentially, we're comparing, different modes of coordination. What if the satellites are more agile or less agile? What if the sensor field of view is like larger or smaller, right? And trying to come up with quantitative results of when something like this actually makes sense. Because the thing is that if your satellite is super agile, for example, right? And the events are pretty slow and you have a lot of time, you don't really need to be super smart in terms of your coordination, right? However, on the other hand, if your satellites are slow and the events are very quick, that's when something like 3HS can really shine, right? Compared to the status quo, basically, right? So that's what we're trying to do and trying to quantify how many more events of different kinds you see with one architecture versus the other. So that's pretty much it in terms of 3D chess. And then this is just an animation of one of the architectures kind of working. But for the last couple minutes, I'll just talk about the other one, the astronaut one, for those in the room that are more human spaceflight oriented. So this one is really about understanding how we can use AI assistants to help astronauts when we're in a long duration mission, far away from Earth, long communication delay. Mission control is 40 minutes away, basically, in terms of communication delay. So you can't really have a conversation with mission control if every time that you say hi, it takes 40 minutes for the message to come back, right? If there's a spacecraft emergency, you need something else. So can an AI assistant basically take the role of mission control is the idea, right? So we developed one of these virtual assistants to help with that. We're focusing on spacecraft emergencies as opposed to, say, health emergencies or something like that. And we're focusing on the ECLA subsystem, so that's environmental control and life support system. So everything that has to do with, maintaining the astronauts alive and happy and comfortable, basically, CO2, temperature, humidity, those kinds of things, pollutants and so on. So we developed the assistant. I'm not going to go into the details because we don't have time, but basically there's a web-based front end with a chat box. There's also a voice interface that you can talk to it if you prefer. And the idea is that, let's see, you can see. So we're going to inject a fake anomaly scenario, right, for those astronaut subjects, right? And then they're going to see that something is off. They're going to have an alarm. They're going to go to Daphne. They're going to see, humidity is above the upper warning limit. They can see the time dynamics of time series of those measurements. And then they can ask Daphne basically for a diagnosis. And Daphne, this is the most basic version in which it will just say, okay, given the signature of this anomaly and given my knowledge graph, I think that this is probably some kind of main cabin fan failure. And then if you click on that, you can get basically a recommended course of action, which in this case, it's just this procedure called main cabin fan activation. You can check the steps, you can ask questions about the procedure. What are the materials that are needed? What are any residual risks if I apply it? Those kinds of things. We also developed our own version of Hera. So this is an Unreal Engine 4 or 5 maybe simulation of the Hera habitat that we use for some lab experiments before going into Hera. So it's kind of like representative functionally of the Hera environment. Of course, it's not super sophisticated, as you can see, but you can interact with the different objects. You can don or dump different pieces of equipment. You can change some canister or something. You can open and close different doors and things like that. Basically, you can execute all of the procedures. What was interesting about this study, what is interesting, is that when we do experiments in the lab, it works really well. We really see huge positive impacts on performance, mental workload, situational awareness. I can send you the paper if you're interested. Everything is significant and nice and everything. When we go to HERA, which is, instead of graduate students being the subjects, now it's, a pilot, a NASA engineer, a nurse, right? Then we don't see any difference, right, between the using Daphne or not using Daphne. It seems like in this campaign that we did, basically they just find the task pretty easy either way. Either doesn't matter if you're using Daphne or not. Mental workload is pretty low, situational awareness is pretty high, and you don't really use Daphne for that. So the idea, so kind of like jumping ahead here, some more lab experiments that we've done to basically show that explanations help a lot when you have incorrect assessments or incorrect recommendation. What we're doing now is basically we're going to do the next campaign, C7 instead of C6, and we're going to do much more complex anomaly scenarios to see, when you have a little bit more complexity, Daphne becomes useful. We also have a little bit more capable agent also that can provide these explanations, that can take initiative and ask questions to the user. And yeah, we're going to see. We'll see if it looks better or not. And we're pretty excited for this. And I think C7 starts January 28th or something like that. I think training starts 2 weeks before that. So in a few months, I should be able to tell you how that went. And yeah, that's all I have for you guys. I think right now the two key words in my lab are autonomy and explainability. So autonomy in terms of we really need more autonomy in our space systems to do the missions that we want to do. And explainability because even, of course, for the human AI collaboration stuff, explainability is critical. But even in the autonomous case, at the end of the day, there's always going to be a human operator, at least trying to make sense of what the hell that sensor web is doing, right? So having some transparency, explainability is also super important. So that's kind of like the two big challenges that we're working on right now in the lab. So with that, I'll stop and see if you guys have any questions.
What information does Daphne have stored to make a diagnosis in like a response?
Yeah, so this is just a knowledge graph that contains about, I don't know, a few thousands of nodes that are things like parameters like PPCO2, PPO2, procedures, anomalies that are known to occur, basically all of the relations between those. So essentially it's like a big expert system that knows that when PPCO2 increases and PPO2 decreases, that's probably something that has to do with the carbon dioxide removal assembly or the Sabatier reactor, things like that. It's like essentially qualitative knowledge about ecosystems and typical anomalies and how to solve them.
Then how often does Daphne make a correct assessment in an operational environment and in a lab environment?
So I mean, this is all, even in the HERA case, it's all concocted by us, right? So we can make it whatever we want, right? We can make it 100% accuracy, or we can manipulate that to basically provide some incorrect recommendations and see what is the effect of inaccuracies, right? So one of the interesting things, of course, and you can probably relate to this, if you have an AI assistant that gives you incorrect recommendations, your trust in that agent is going to degrade, right? So, seeing how to repair trust, for example, is one of the things that we're looking at, right? Another problem that we have is over-reliance. So sometimes, Daphne works at the beginning, so people kind of like extrapolate and assume that she's always going to be right, right? So that kind of over-reliance is also a problem. So we talk about trust management, basically, and trust repair. But yeah.
Would a fair analogy that Daphne kind of serves as like project controls for like the procedures to get through the big stuff?
Yeah, I mean, it's really trying to take this role of mission control, right? So, but of course, it's not a human. It's still pretty unsophisticated AI, right? I mean, it's just a database of knowledge, right? And a way of querying that database in a very fast and efficient way. But that's all there is to this, right? So yeah, it's about, okay, so oh, I see these symptoms, what could this be? Oh, this is probably, the Sidra or the Sabatier reactor. Go and take a look at this and see if the filter is clogged or something, right? It's that kind of capability. It's not like, like a all-knowing or whatever AI, right?
Yeah.
So more or less, the system is not able to connect to the internet. It relies on the stored information it has.
Yeah, so this one is a completely closed world, so it will refuse to answer anything that's not directly related to the content of its knowledge graph. That's a very interesting question that you're asking because now we have, of course, ChatGPT, right? And ChatGPT actually, the one that we have now has changed substantially from the beginning, and it's now starting to be, a little bit more careful with the answers that it provides, right? But it used to answer anything, right? And very confidently and with no problem, right? That's not what we want for something like this, right? We want something that has very high reliability, right? And if it doesn't know the answer, it doesn't know the answer. That's fine. But yeah, the other challenge with connecting to the internet is, of course, latency, right? I mean, if you're 40-minute communication delay from mission control, you're probably 40-minute delay also from the internet. And you could do like periodic updates and things like that.
What are you using to gauge trust in humans with the AI systems?
Yeah, that's a very good question.
Questionnaires
There's a lot
or-
of literature in that. So there's like objective measures and subjective measures. Pretty much when people use these surveys, honestly, questionnaires. So there's different kinds of questionnaires, trust in automation, essentially questions, how much do you think that you can trust this agent, or do you think that it has deleterious, or that it has I don't know, bad intentions or whatever. I mean, there's like different questions, and there's like a Likert scale kind of thing, like how much you agree with that statement, and then you do the average, and you get a number. So I mean, there's actually very interesting work right now, looking at more objective measures of things related to trust. Trust is a very complex construct, right? But looking at things like speech, the words that you say, the intonation, like how you say them, doing things like sentiment analysis, speech processing, and trying to correlate that with trust. So yeah, I mean, there's a lot of different kinds of work right now trying to understand trust better. Yeah.
Does the judiciousness of the person like affect the trust level? Because like I know we took like Maya character studies, so I was like my number one like personality trait was like judgment, basically like the fairness, right? Like when you go in there and like let's say you have an astronaut and like maybe they don't like AIs for some reason, like they're more likely not to.
Absolutely, yeah. I mean, there's different, again, trust, very, very deep area. There's different types of trust, and one of the types of trust is essentially completely driven by your previous experiences, preconceptions, or AI and these kinds of systems, right? And that plays a huge role. I mean, we've seen it in Kara, right? And actually, we've seen it's very interesting. This people have different backgrounds and such, right? And somehow it seems like masters of science compared to bachelors and PhDs seems to be like the optimal in terms of like performance in our studies. And engineers, I forget all the details, but there's some interesting trends basically showing some correlation between not just performance, but also amount of trust, this kind of dispositional trust, based on like, are you an engineer or not an engineer? Do you have a bachelor's, a master's, or a PhD, things like that. Right? So it's pretty interesting.
Do you have a paper on that?
Yeah, we do. Well, the individual differences, not yet. It's in the works, but we have a few papers related to all of this. The C6 paper is a little bit disappointing, as I showed in the results, but the two lab experiments are pretty cool, pretty good, pretty strong results.
Do you all have any theories as to why they didn't align?
Yeah, we do. I mean, there's a lot of things going on, right? So first of all, there's the timing of the whole thing, right? So in the lab experiments, you have 20 minutes of training essentially, right? And then you do a few tasks that go very quickly, the whole thing is over in a few hours, right? In Hera, it's a 45-day thing plus 2 weeks of training, right? And granted, it's not all training for our experiment, but the whole timing of things is just slower, right? Then it's more, people with higher experience, just older people, more experience, more operational experience also on average, right? And then a big thing also is that it's basically the control condition. So the control condition in our experiment, they had essentially the manuals, right? So they had a 10-page document that basically talked about the subsystems and how it works, right? Which we think is basically more representative of reality. What they had in Hera was basically a table, and the table tells them directly, if you see these symptoms, you should do this procedure, right? So it's very direct what it needs to do, right? And they were a little bit like, I don't know, risk averse with us changing some of the things that they do. So they didn't let us change any of that. And we think that could have played a role also in terms of, because that's a very direct, answer to the problem that we were giving them, right? So yeah. We'll see. With C7, we'll have more complex scenarios, and hopefully, we're in negotiations also for they call it the anomaly chart. We're trying to make it at least a decision tree, so it's not as direct. So we'll see if that helps too. But we're just trying to understand, right? Because at the end of the day, you can't have a table that tells you what to do in every possible situation, right? That's just not, there's always going to be something that you didn't know that was unplanned, right? And that's also true for the agent, right? The agent right now is just a knowledge graph, right? And the knowledge graph can never have everything that can possibly have, right? So at the end of the day, is about having something that helps you with information retrieval, information processing, organization of the information, and it helps you make a decision, basically, right? You don't know if the decision is the right one, but it's a decision support tool. It's not really, again, it's not an oracle.
Is there any thoughts on the work to make it more self-learning for further, like longer duration?
Yeah, I mean, there's of course a lot of work in terms of machine learning these days, learning from, the thing would be collecting data. We're not doing that, right? But the thing is connected to the telemetry feed from the spacecraft, right? So it's collecting, a huge, super long time series for 50 parameters, right? And it also could have potentially labeled data. It would be pretty easy to label the data by saying this is nominal, this is not, right? Even if you don't want to rely on like anomaly detection, like outlier detection, trend detection, kind of wrong with that, right? So, and then it could be like, we could also have reinforcement pretty easily, right? Like a thumbs up, thumbs down with what Daphne says, for example, right? So there's different ways in which you could learn. That would be fairly cheap in terms of providing the data. But yeah, we haven't really, it's all about, at the end of the day, in research, it's all about the money too, right? I mean, we need money to do that. Lots of ideas, but if you don't have the money, you can't do anything. So.
When it comes to the satellite communication projects, is there a way for a group of satellites to determine which task is more important if it gets like 3 task requests at the same time?
Yeah, so and that's a kind of like a loaded question, because there's the question of more important to whom, right? So it really depends on, there's different settings. So one setting is kind of like the cooperative setting where everyone is on the same team and there's like a global utility function that you're trying to maximize. And then at that point, it's very clear, you can have a definitive answer to what is the most important thing to do, assuming that you have the right models. The more interesting and complicated case is the federated case, right? I'm not going to go into the non-cooperative case because again, we haven't done anything related to defense, but even in the friendly case of, say, you have some NASA satellites and some ESA satellites, right? They are operated and owned by different organizations, right? They have their own goals, their own utility functions. So when you say the most important is it the most important to NASA, to ESA, or to global welfare? What does that even mean, right? So there's some complications to that, but yes, they definitely have the ability to choose between competing tasks in terms of some scalar utility function, if you agree as to what that should be.
Have you all done any work in terms of how to include humans in the task allocation column, like humans and robots?
Not really, I mean, you know, you can think about the human as a source of task request. That's kind of like the obvious choice, right? You could think about the human as a node that only does data processing also. But at the end of the day, the problem with those things is, you know, I think having the human as a task request generator is never a problem, right? But having the human in the loop for like the response to an event of interest is challenging, right? Because it's the bottleneck, right, for a lot of data processing and things like that, so. You guys? Cool, all right, thank you all.
Get a round of applause from Mr. Salt.
Don't forget to come out, watch some rockets on Sunday.